In this second video segment, we are looking at the most basic dynamic control method for robot arms, which is on one side joint impedance control, and then as a second step, inverse dynamics control. For all the dynamic control methods that we are analyzing and introducing in the future, we need to have a look at the dynamics equations of motion. So I'm going to keep these here on the top right. And what we're doing is we are manipulating this in such a way that we can generate a desired torque that we're sending to our actuators based on desired motions that we have in our system. Now, as you know, the most simple setup is similar to the kinematic control of systems that we looked at position offsets and defined then joint level velocities. Now, what we can do here is that we look at tracking errors, position errors and velocity errors, and define a joint torque which is based on these tracking errors. So that means we have a desired torque, which is nothing else than a P gain times a position offset and a D gain times a velocity offset. If you look at the physical embedding of this controller, then this is nothing else than a spring damper element that mount into every single joint. Now what you can do is we can analyze the feedback behavior, the closed loop behavior of this system. So we write the dynamics equations of motion on the left hand side, and we know that our torque is given by this PD controller. So we have a Kp times position and Kd times velocity offset. Now what is obvious here is that this thing has a stationary offset, so static offset due to this gravity part. Because if we are not moving the system, we have the acceleration part being 0, the Coriolis centrifugal part being 0, and also like this tracking error between the desired and actual velocity is 0. So we have a direct relationship between the gravity here, which produces a joint level offset to the nominal configuration that we want to achieve. And that's also intuitively clear. So if you take this robot arm, you have only spring damper elements in the joints, you let it go, what it does, it will slightly oscillate around and then find itself in a new equilibrium where this offsets in the joints times the stiffness will produce the torque that corresponds to the gravity compensation of the system. Now, there's different ways how you can compensate for that. One way would be to add an integrator term in our controller, but of course, as you know from controls classes, this will compromise on the stability. The other way is that since we know this gravity part, we can actually actively compensate for that. So all we need to do is we have to bring this somehow to the right hand side into our controller. So if we can formulate this an impedance controller including gravity compensation, which then simply looks like the torque being the P gains times the offset in position plus D gains times the velocity error plus a gravity compensation term. Important now is that we have here a HUT. This HUT means that it's an estimated gravity term. We will never be able to perfectly model the actual robotic system. So that means there will still be some offsets here just because of the fact that the model gravity doesn't really correspond to the actual gravity in our system. Now this setup is very simple. There is one problem though, namely that it is configuration dependent. So what does that mean? So imagine you have this robot arm here on the right. If you look at the configuration as it is drawn like now, you have a spring here. The spring sees a center of gravity which is somewhere here. If you would stretch out the arm now to a configuration like this, you might have a center of gravity of the complete arm around that joint here, which is somewhere out there. So in other words, this spring here, this one always sees, depending on the configuration, a different load while having the same stiffness, the same P gain. And that of course changes the natural frequency and hence also the control performance. In order to make it independent of the configuration, one can make a step further and use inverse dynamics control, which means that we're not only compensating for gravity, but we're also compensating for the mass times acceleration and for the Coriolis centrifugal part. So that means if you're defining now the torque based on the complete system dynamics, and we assume that we have no modeling errors, then the closed loop dynamics of our system looks just perfectly like identity times acceleration is equal to my desired acceleration. So in other words, this means that if I'm taking a PD law and I define that my desired acceleration is in essence a position gain times a position offset plus a velocity gain times a velocity offset, I get a behavior which is completely decoupled of the configuration. We always have the same inertia properties, so every joint in this configuration behaves like a decoupled mass spring damper system with unitary mass. In other words, I can go now and define these Kp's and these Kd's as a function of how I would like the dynamics to look like, depending on the frequencies, that the natural frequencies of that system, and also whether or not I want to have things be overcritically damped, undercritically damped, and so on and so forth. So this makes inverse dynamics an extremely powerful tool, and you can achieve really great performance without adding any integrators to our system, just by purely having model-based compensation of the dynamics. However, what is necessary that we require a very precise model of the system. So the more precise we are, the better we can compensate, and of course the more accurate we can track the desired feedback dynamics. However, in reality, obviously there is modeling errors, in particular modeling errors and the hard to model parts in B, which makes this approach not that easy to apply. Now, so far we only looked at inverse joint space dynamics, so we directly predefined the Q double dot as a function of joint space offsets. However, in a real world problem, it's often not that easy to define the motion in joint space, but you rather want to describe it in task space. And as you've seen in kinematics, there is a direct relationship between joint level motion and task level motion or end factor motion, which is given by W dot is equal to Jacobi times joint space acceleration and Jacobi dot times joint space velocity. Now what one can do is, if you have a single task, is that you just solve this for Q double dot, which is then equal to the pseudo inversion of J times W desired minus J dot Q dot, and then insert this up there. However, in complex machines, very often we want to fulfill not only one task, but we want to fulfill multiple tasks, and we also know how to do this. We can use the same pipeline that we introduced earlier for velocity control. We can either give individual tasks the same priority and then do multitask inversion, which is in essence a stacking of the Jacobians, you do pseudo inversion of that, and then you stack also the desired task level velocities. Or you can do it in a hierarchical manner. You say, like, my tasks have different priority and I only want to fulfill the second task as long as I'm not sacrificing on the first task. And you see here again the iterative formulation that we introduced for that. So for the complete joint level desired acceleration, what we do is we take the null space projector for every task, respectively its higher level task descriptions times the joint level, or the acceleration, the task level acceleration, and every task acceleration is given by the pseudo inversion of the task Jacobian multiplied with the projection matrix, the null space projection matrix of the higher level tasks times the task level acceleration here. So it's W dot minus the coupling term minus the contribution of the solutions of higher level tasks to this corresponding task. And then what you're doing is, like, once you have either the Q double dot coming from the same priority optimization or for the hierarchical optimization, you take this and you insert it into your inverse dynamics formulation. Now we would like to end this video segment with a small quiz. We're looking at again at the same excavator that we had in previous video segments, where we have generalized coordinates described by triangles and one linear degree of freedom. I give you the equations of motion, which we derive using the methods from the last lecture. And then we have also given you the end effector position rotation Jacobian, so you can use all these variables in the following formulations. And what I would like to do is, first of all, think about the dimensionality of the problem. So what is the dimensionality of JP? What is the dimensionality of JR? And then go into the following questions. First question is, what joint torque is required in order to achieve static gravity compensation? So assume you want to have this arm up in the air and stationary, and I ask you what kind of joint level torque and forces is required for that. Second, how much is that if you have to additionally lift 100 kilo in the bucket? So at point P here, we have 100 kilogram of weight. And then see what torque is required in order to accelerate with 1 meter per second square upwards. And by doing so, you want to keep the orientation and the x position constant. So that means the orientation of the end effector, the acceleration is 0, and the acceleration in x direction is also 0. And then lastly, question is whether or not the solution that you figured out here is unique or not.